Voice of the Sea, learning from experts across the ocean.
Welcome to Voice of the Sea.
This time on Voice of the Sea, we're at the SOAS biannual open house.
Let's start with this one. This is a sea glider, and it works by changing its density, so the volume mass divided by volume. So it sucks oil back into the pressure case here at the surface, so this goes inside here, and then it makes itself heavier, and as it sinks it generates lift on the wings, giving it forward momentum. Then at the bottom it pushes the oil back out of the pressure case and inflates the bladder, making itself have more volume and therefore floats, and again generates lift on the wings, and so it can run a sawtooth like that, and then when it gets to the surface it sticks this antenna out of the water and gets a GPS location and calls in through the satellite phone network and uploads its data.
Very cool.
And it can, then it just repeats up to about 6 to 8 months, can stay out.
So density is one of those concepts that's really difficult to understand. You learn it so many times throughout school. Can you explain that one more time, how the sea glider changes its density, allowing it to do that depth profile? So
there's two ways that density can change. Either the volume changes and the weight stays the same, or the weight changes and the volume stays the same. So if we head over to where Kelly is running away from. So these two are both 3 ounces, and so but obviously the wood is much bigger, has much larger volume. So we put them in, one sinks and one floats. And so, where'd they go? This apparatus works a lot more like the glider. So it weighs the same. We're just moving the bulldog clips around. So it still weighs the same, but this inner tube has inflated because the air has come back out of the bottle and is now in the tube. So in this configuration, got the larger volume and the weight remains the same. It floats.
Okay. And then can I change the volume by moving the clips?
Yeah.
So I'm just going to take them off the back.
And crimp up the inner tube.
And that's changing the volume.
That's changing the volume, but because you haven't added or subtracted any bulldog clips, the weight remains the same.
So I predict that this is going to sink now.
Yeah, provided you didn't stick too much air in it. But this is an Argo float, works on the same buoyancy principle. So this is a flooded region down there, and so to sink, it retracts a piston, making itself have less volume, and then it sinks. This one goes down to 1,200 meters, but there are Argo floats out there that go as deep as something like 2,000 meters.
Wow. They
sink down, they spend about 10 days floating at that depth, so you get the current at, say, 1,200 meters for this one. Then they come back, make themselves buoyant, come back up, and sample the temperature and salinity in the ocean on the way up, take a GPS location, and then phone the data in through the Iridium network, and then start all over again. These can last about 5 years, and
wow,
there's about 3,000 of them out in the ocean at the moment. So these are the locations of them as of yesterday, the 20th of October. And so you can see that they're reasonably well distributed throughout the ocean. There is more of them sort of getting caught up. They bunch together when they come up by Japan. It's a Kuroshio current. The same thing would happen. It doesn't appear that it's happening terribly strongly with the Gulf Stream on this side, but eventually all these ones will sort of bunch up in the western boundary conditions and then get spit back out into the middle of the gyres.
So that's a little bit mind-boggling every single dot on here represents one of these Argos
It represents
floats
one of those floats, yes.
in real time. So today there's you said 3,000
Yeah,
out around the world.
So these dots represent the last time, where it was last time it came on the surface. So some of these dots could be up to 10 days old because they spend 10 days at depth. But yes, this is the number of Argo floats that are out there at the moment.
And that just seems like almost a nightmare of data that you're going to have to be able to analyze. How do you deal with that much information?
Well, it's only taking temperature and salinity. I'm not actually involved in the Argo program, so I'm sort of just extrapolating.
On its behalf.
But it's only collecting temperature and salinity data on the way up. So, and then it has to be a small enough amount of data that it can be transferred through the satellite network. You don't recover these things, so all the data you're going to get back from them has to be sent back through the satellites.
So what happens when it's lived its life?
They scuttle and sink. There is a central place it all goes, and I think it's all available in near real time on the web. This is the Argo website there. You can find more information. And it's used by a number of different people to look at all sorts of information. A lot of it is ingested into numerical models, simulations of the ocean to give them better accuracy. Also a lot of detailed studies of one particular process that it's used for. So it's freely available and is used by lots of people for lots of different things. So this is Rockland VMP, Vertical Microstructure Profiler. So it measures very small scale, sort of half-inch scale temperature and velocity and salinity variations in the ocean. And so the front end here, you have places for 6 sensors, normally 2 shear of velocity and then salinity and temperature. So the probes are this size, so a little more than, what's that, about an inch. And these are the velocity or the shear probes. So they measure the velocity fluctuations in the ocean as you go down. Inside one of these probes, there's essentially a phonograph needle. So it's measuring the vibration in this axis, the narrow axis of the beam. And then as that wobbles, it generates a current that is recorded by the instrument.
And that's how it knows how fast it's going?
That's how it knows what the fluctuations around some arbitrary mean are. So we're only sort of interested in the small scale fluctuations. The instrument itself falls at about half a meter a second, but that's kind of irrelevant for what these are measuring. This is a broken temperature probe. So actually the sensing element is a little bead that should be on the end here. So if it was on there, it would be hard to see. So it's measuring at very small scales. So this instrument is designed to go to 6,000 meters. So it has a very heavy pressure case. This tube here is about 1 inch thick all the way around. And then the back half of the instrument is all flotation to counteract the weight of the pressure case. So that in this total form, it is only it's about 14 pounds or so positively buoyant in water. And so to operate it, you stick, actually, okay. Yeah, awesome. So you stick 2, well, in this case Coke cans, but 2 14-pound pieces of steel bar on it. When it gets to its target depth or pressure, then it drops the weight and is now positively buoyant, comes back up, and because it was never attached to the ship after it went overboard, then you have to, it just floats to the surface and you have to go and find it. For that we have a bright orange flag that's down there, and we also have a flasher beacon for operating at night. We have a radio directional finder and a satellite beacon in case it gets horribly lost.
Very cool. So I understand measuring temperature and salinity, but can you go back to measuring the speed of the ocean? What do you mean by that? It says on here, it says speed of the ocean.
That's he wrote the poster. So that's the small scale fluctuations in the speed of the ocean. So all of these are very small scale fluctuations of how things vary over, less than a second and over less than an inch type scales. This instrument can measure the larger scale velocity in the ocean. This ring here is an electromagnetic current meter. So this whole instrument rotates as it falls down through the ocean. It's not in there at the moment, but and as it rotates, the electrodes there measure the velocity generated by something rotating in the Earth's magnetic field. And from that, you can calculate the horizontal velocity of the fluid that it's moving through.
Gotcha. And is this something that you're using in your own research?
Yes.
And what is the scientific question or observation that you're trying to get at?
We are trying to get at how the ocean mixes. So the ocean mixing is important for mixing fresh water down and salt up, sort of to complete the global circulation that takes 1,000 years or something on that order. And it's also important for mixing pollutants and that and diluting them. It's also it's very spatially variable, and both in the horizontal dimensions and vertically. So, and it's changing in time. So, but it's also very important for sort of global models, and it's one of the parts of a global model that is least well known, and generally, well, it always occurs below the resolution of the numerical model. So below because numerical model you couldn't run with current computing power at the sort of level that at this sort of centimeter or half-inch scales. So they have grid cells that are quarter of a degree or a couple hundred meters apart. So this is always going to occur below what you can resolve in a global model. And so the idea is to parameterize or get a relationship between the mixing that's occurring and the larger scale things that you can produce in a numerical model. And the feedback between them, how the ocean mixes is actually quite important for the larger scale stuff. So there's still not a whole lot of this data, so we're collecting data under different conditions, or in order to get a better feel for how the ocean mixing is related to larger scale processes. So the cruise we just took this out on late last year, end of 2010, was looking at what are called internal waves, or fluctuations of interfaces within the ocean. And so there's a big source of those on the Hawaiian Ridge, and we were looking at what happens to those waves when they interact with topography downstream. So we were looking at sort of the scattering of those internal waves and the dissipation that produces, because the presence of internal waves at those sorts of scales is something that is conceivably modeled in a global model. So where and how those cause dissipation is something that we could parameterize in the future.
Very cool. So people used to in textbooks you used to read about like thermohaline circulation, and now some scientists are saying that that's not an accurate way to portray like a Glober conveyor belt type of idea. And is that relate to what you're studying?
That's the larger scale picture. It doesn't relate directly. This is a small scale component of it. The conveyor belt is definitely a simplification of what's going on. And I think that's what a lot of people have against that particular description of it, that it's way too simplified.
And certainly if you're looking at these really, really tiny scales and seeing fluctuation, that speaks to the fact that this Glober conveyor belt idea is a simplification.
Yeah, I think, yeah.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
NOAA Pacific Services Center, linking people to information and technology. The Pacific Services Center wants you to be prepared for any weather emergency and know your tsunami risk. NOAA Pacific Services Center, enriching life through science, service, and stewardship.
Exploring Our Fluid Earth is the dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group. The award-winning Fluid Earth and Living Ocean textbooks are now interactive and online. New activities, updated content, and a teacher community. Exploring Our Fluid Earth is now freely available. Find out more at exploringourfluidearth.org.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community from elementary to graduate students. Hawaii Sea Grant.